Hello and welcome to this new video. In the previous videos, we have integrated the player progression system into the game. In this video, we will discuss a new topic. It is the player data storage. The data storage service for a player consists of persisting game data concerning a player. The objective is to keep certain data on the cloud that the game can restore for a player if this player reinstalls the game or if he connects to his account from several machines. An example of use of this service is to save elements of the game on the cloud, such as the player's score and the objects he has unlocked. It's up to you to choose which game elements to save on the cloud for each player according to your game. In this video, I will show you how to use and integrate this service into the game. I will implement as an example the saving of the game on the cloud. I want to save the position of the player in the match locally, then synchronize the local save with the cloud. This allows the player to load the save from the cloud and therefore complete his progress in the match from the last saved position. We will see how it works if he loses his local save and how our implementation loads the game from the cloud. To start, we need to implement the logic allowing the player to save and restore the game from a save game object locally. A save game object is an Unreal Engine object allowing to define data to save and restore locally. In this object you can define the data you want. It finally depends on your game and your objective. In my example, this object will only contain a 3D vector representing the world location of the player in the match. I choose the example of storing a save game on the cloud because it is a good example that is useful. I can instead do a simple thing such as saving a variable on the cloud without having to go through a save game process. The goal is therefore to show you a useful thing. Note that the player data storage service allows you to save any data you want and that it is not limited to an object such as the save game object. In the main menu folder, create a new folder that will contain the save game object. In this folder, add a new blueprint class of type save game. It is in this blueprint that we must add the data to save. As you see, it is a normal blueprint like the other blueprint classes, except that it has the particularity of representing a save game object. Now go to your game instance. I want to implement a system that is used to load the game from the save game object automatically if this object already exists and to create it if it does not exist. What I mean by if this object exists is to draw your attention not to confuse between the save game blueprint that we created and the save game object created locally using this blueprint. In other words, the file added to your project by Unreal Engine when creating the save game object. Add a custom event that runs on the client and is used to create the save game object if it does not exist or to load the game from this object if it exists. To know if the save game object already exists or not, then we call the node does save game exists. We will base on this node to decide when we must do a load and when we must do a create. The slot name is a name that you define to organize your save game objects. We will use the slot name to identify the object that we must load. In this example, I want to work with a single slot. Note that you can create several save game objects and therefore use several slots. If the save game does not exist, then we must create the save game object. This is done by calling the node create save game object. For the save game class, we give the blueprint class that we created. This node returns a reference of the save game object created. Once the save game object is created, we must save the game using the reference to the created object, so call the node SaveGame to slot. Make sure to give the same slot name that node does SaveGame exist uses. Connect the SaveGame object pin to the reference returned by the create node. This implementation adds a file representing the SaveGame in your project directory. Promote the reference of the SaveGame object created to a variable. We will need it. If the SaveGame exists, then we must do a load instead of create. So call the node loadGame from slot by providing it with the slot name that we have defined. Update the SaveGame variable by giving it the reference returned by the load node. We see that the variable is of type BP SaveGame. It is because of the promote made after the node create which takes this class as a parameter. Therefore change its type so that it is of type SaveGame object, which is the parent of our class. To test the implementation, call this event once the game instance init is triggered. Go to the saved folder of your project repository to see what will happen when you launch a client. And there you have it. Once the game instance is initialized so the custom event is called, we see a new folder in the saved folder with the name SaveGames. In this folder you will see a file with the name of the slot that we defined and which represents the SaveGame object created by our code. Note that the creation process is only done if the SaveGame does not exist, so if you launch the client again, the load process will be called. Return to your game instance. I want to add a function in the game instance interface that is used to return the SaveGame object reference. This allows us to interact with the SaveGame object from any blueprint object. Once added, go back to your game instance to implement it by giving it the SaveGame variable. Now go to the SaveGame folder. we must add a blueprint interface which will be implemented by the BP_SaveGame class. This allows us to interact with this class to update the data that we must save. For the example of this video, this interface will contain two functions. The first is used to update the value of player position, and the second is used to obtain it. The player position is a variable of type 3D vector. Go to BP_SaveGame to implement the interface we created. To implement the setPlayerPosition function, simply create a vector type variable and then set it when this function is called. Add in the interface the function which is used to return this variable. Implement this function by connecting the variable. We will use the SaveGame object reference and this interface to save the player's position in the game. I want to implement this logic when the player plays World 1. For this I will implement an automatic save logic in the player controller of World 1. You can of course do it manually and in any object. In the player controller of World 1, add a custom event which runs on the client and which is used to save the world location of the character. We need the SaveGame object reference. We can get it from our game instance. Using this reference, we will call the SaveGame interface function which is used to update the player's position. To get the world location of the character from the player controller, we must go through the controlled pawn. Once the variable is updated, we must save the game, otherwise, the value will be updated, but this change will not be saved locally. Make sure you use the correct slot name. I want to call this event automatically every 2 seconds. You can also call it from the UI if you want to allow the player to do a manual save. So I want to call it once the pawn is possessed using a timer. I want to add now a second custom event which is used to load the player position from the save game object. The objective is to spawn the character at the last saved position each time the player starts a World 1 match. Get the save game object reference from the game instance. Use the save game interface function, which is used to return the player position. We should not change the position of the character if the position has never been saved. This will be the case for a first match launch. We must load the position before starting the auto-save process, otherwise the last saved position will be replaced by the player start location. I want to add a short delay to make sure the position has been loaded before starting the autosave. You can use an event dispatcher instead as a robust solution. For a test purpose, I want to display a message on the screen indicating whether the save was successful or not. Launch a client to test the implementation. To be able to play World 1, I have to create a lobby session because our implementation does not allow to start the match if the current session is not valid. And there you have it. The first launch of the match, the character is spawned at the player start location because the position is not yet saved. We then see on the screen the message indicating that the position is saved. Move the character to check that its new position will be loaded in the next match. Quit the match, then start a new one. And there you have it. The last saved position has been loaded. Move the character, then repeat the process. And there you have it. The load and save system works as it should. Quit the game, then go to the saved folder to delete the local save. Launch the client again to start a match. The save game object has been recreated. Start a new match. Here, the player has lost his progress in the match because the save file has been deleted. To avoid this problem, we will make a remote save via the player data storage. Integrating the player data storage into the game means allowing the player to read and write files on the cloud service provided by the target OSS. As we have already done for the other services, I will implement this system in the master player controller so that it can be used from all child player controllers. Search for the word player data to get all the features offered by Easy OSS Plugin regarding the player data storage interface. Basically, these features allow you to read, write, and delete files on the cloud. Use the task Write OSS Player Data file to write a file to the cloud. This task takes as parameters the file name and the file contents. The contents is a bytes array. Note, the Unreal Engine Player Data Storage interface treats files as binary content. In other words, we do not work with file formats and extensions. So all file types must be converted to binary data. Add a custom event that runs on the client and is used to write a file to the cloud. Connect the task pins to the event. Add an event dispatcher that tells us if the task is executed successfully or not. It's just to draw your attention that you must call an event dispatcher following a task if you want to implement a retry system or if you want to be notified. I don't want to use it in this video. Go to the Master Player Controller interface to add the function that is used to execute this event. Add the corresponding inputs. Implement this function by calling the custom event. Display an error message if the task fails. Go to the player controller of World 1 to call the file writing process. Normally, you have to save the game to the cloud after each local save. We need to convert the save game object to bytes array because the write process only accepts binary content. Unreal Engine does not offer you any blueprint node to do this, while the plugin offers you nodes to convert objects to bytes array. Call the interface function to write the file. Choose a meaningful file name. Under the Utilities category of Easy OSS Plugin, you find nodes that allow you to serialize and deserialize objects into bytes array. The serialize converts the object into bytes array and the deserialize converts the bytes array into object. The plugin allows you to serialize and deserialize vectors, strings, floats, and save game objects. For example, this node allows you to serialize a string to bytes array. This node does it for a float. And that for a vector. What we are interested in is the node serialize save game object to bytes array. You can use the other nodes for other purpose, such as saving player score to cloud. Note that you can do all this from a save game object which can contain lots of information. Connect the save game object to the node to serialize it to bytes array. Connect the output array to the input file contents. Note that we do not save the game on the cloud if local save fails. Launch a client to test the implementation. Go to your dev portal, then look for the EOS Player Data Storage tab. Copy the client's product user ID to search for his files written to the cloud. As you see, we have no files in the cloud concerning this client. Start a World 1 match. Wait for the save process to begin. Go back to the dev portal and search for the client files again. And there you have it. We have a new file written which represents the save game object, so we have successfully saved the game to the cloud. We now want to allow the player to load the game from the cloud. Go to your game instance and look for the custom event that we created and which is used to create or load the save game object once the game instance is initialized. What I want to do here is to change the implementation, which is to create the save game object if the save game does not exist. So instead of directly creating a new save game object, we must first check if the player has a save game object on the cloud. In this case, the priority will be to load the remote save game object instead of creating a new one. Call the task load OSS player data files. This task returns you the list of file names of the local player on the cloud. To know if the player has a cloud save or not, we must check if the list of file names returned contains the file name representing the save game object, which is in our case the name of the slot because I chose the name of the slot as a file name when writing the file. If the file is not found, then a new save game object is created. If the file is found, then we must read its contents. This is done via the task read OSS player data file, which takes the file name as a parameter and returns a bytes array representing the contents of the file. We must convert the bytes array to a save game object. This is done via the node deserialize bytes array to save game object. I draw your attention that you must choose the right deserialization node. There we are sure that this file represents a save game object. Duplicate these two nodes to update the save game variable and to save the game according to the remote save game object. For a test purpose, I want to display a message on the screen that tells me that the backup has been loaded from the cloud. There, if the save game exists, I gave the load priority to the local save game object. You can give priority to the remote save if you want. If the reading task fails, you may need to retry the process. To keep things simple, I will proceed to the local creation of the save game object in this case. I do the same if the load task fails. It should be noted that the player data storage service requires an authenticated user, so the tasks we use in this event will fail if the event is called by an unauthenticated user. For this, we must move the call to this event because we currently call this event once the game instance is initialized, and therefore before the player login process. We can call it there when the login status changes, so when this delegate is triggered by the OSS backend. To be able to test the load of the save from the cloud, we must delete the Save Games folder in the saved folder of the project. This allows the node "Does save game exists" to return false and therefore to prioritize the load of the save game object from the cloud. Once deleted, launch a client. Here, once the user is logged in, we see the message on the screen which tells us that the save game object has been loaded from the cloud. Start a match. The expected result is to spawn the character on the last saved position. And there you have it, that's exactly what we see. If you restart the game, then the save game object will be loaded from the local machine because the save game object exists. And there you have it, everything works as it should. We have managed to use the player data storage to save the game data, like that if the player reinstalls the game or if he connects from another machine, then he does not lose his progress. The player data interface has a delegate that is triggered by the backend when writing a file to the cloud is progressing. It is useful to use it if you want to show the client a progress bar when he writes data to the cloud. This delegate returns the number of bytes written and the corresponding file name. I just want to display the number of bytes on the screen. The task Cancel Write OSS Player Data file allows you to offer the client the possibility to cancel the writing of the file. It is useful when you write a large file. I will not use it in this video. Both nodes Clear OSS Player Data file and Clear OSS Player Data files allow you to empty the set of downloaded files. This is useful to free up storage space on the client machine after reading the files. The difference between the two nodes is that the first one takes into account a specific file, while the second one does the clear for all files. The Delete OSS Player Data File task allows you to delete both a remote and local file. This is useful when you want to free up remote space when remote files are no longer needed. The Request OSS Player Data Usage task returns you a player's remote storage usage. This task is not currently supported by EOS. I want to implement these three processes in the master player controller. As we did for the writing process, add a custom event which runs on the client and which is used to cancel writing a file. Again, you should add an event dispatcher to call that can inform you of the execution status of the task. Add a custom event which is used to request the player data storage usage info. This operation is not supported by EOS. I add it for other OSS. Add a custom event that is used to delete a file. Go to the Master Player Controller interface to add the 3 functions corresponding to these 3 events. For each added function, implement it by calling the corresponding custom event. Go to the player controller of World 1. After each writing on the cloud, I want to request the player data storage usage info. It will not work for EOS, but it will for other OSS. To test the deletion of the remote file, I want to do it in the end play event. I delete the file locally and remotely. Launch a client for testing. Start a match. Here we see the number of bytes written following each writing of the file. As a reminder, it is displayed by the delegate triggered by the backend. We see in the client log that the request for player data storage usage info is not supported by EOS. Click on Leave Match to execute the end play. Go to the dev portal and search for the client files. And there you have it. The file has been deleted following the execution of the delete process. I want to disconnect the call to delete. It was just to show you how the process works. To conclude, the player data service is used to save useful data that is related to the player account. In this video, I showed you an example on saving the game remotely. You can use the service for other purposes such as saving user settings, user score, user unlocked objects, etc. That's all for this video. See you in the next one.